Hey everybody, it's Tuesday, March 16th, and as you can see here in the aim today, our goal for today's video is all about how we can apply our understanding of energy to rotating objects. So as you can see here, like I mentioned at the beginning of this unit, within the rotation unit, we're really following the progression of the topics that we've been doing all year long. We started out talking about kinematics, then we got into forces, now we're ready to talk about energy. But before we get to talking about energy, I just want to take a look at the problem I assigned to you at the end of the video yesterday. In yesterday's video, we talked about Newton's second law of rotation, which is pictured up there at the top right-hand corner of the screen. The torque is equal to I times alpha. This is pretty much just a straight-up translation of Newton's second law, F equals ma. Torque is the rotational version of force. Rotational inertia is the rotational version of mass. And of course, alpha, the angular acceleration, is the rotational version of linear acceleration. And so we needed to use that equation to solve this problem. Now, this problem did have three parts. I only told you you had to do the first two. Of course, I'll show the work very briefly at the end for part C, but let's talk about how you would do the first two parts. If you remember, this question says, a large grinding wheel in the shape of a solid cylinder of radius 0.330 meters is free to rotate on a frictionless vertical axle. A constant tangential force of 250 newtons applied to its edge causes the wheel to have an angular acceleration of 0.940 radians per second squared. The question here is asking you, what is the moment of inertia of the wheel, in part A, and then in part B, what is the mass of the wheel? Now, you really had to be clever in figuring out and interpreting all of the detail given in this problem. Again, as well, I think this is a good example of a question where you're going to want to look at all the parts, because your first instinct when you see a part of a question that says, what is the moment of inertia of the wheel? Your first instinct might be to go to the moment of inertia reference sheet and just look it up, because they do tell you here it's a solid cylinder. You can't do that, though, because as you can see, they don't give you the mass. And that's really because that's what they're asking you for in part B. So here, we needed to use all of the information given in the problem to really be able to figure out what's going on. So obviously, as is always the first move in solving any problem, let's make our list of knowns. They tell us here that this thing has a radius of 0.330 meters. And they tell us there is a force applied, and it's a tangential force, that's a big hint, of 250 newtons. They also tell us here that the angular acceleration of the wheel, if you forgot, was 0.940 radians per second squared. Now, let's just address one thing straight away, because it's actually going to be the first thing they're going to do. Why are they telling you this? Why are they telling us it's a tangential force? The key thing to recognize here, to start this problem off, is you have enough information to be able to calculate the torque. We know the force. We know the distance that force is applied from the rotational axis for this object. And the fact that they tell us it's tangential means we now know there's a right angle between the force and that position vector r. And so that means we can also include in our list of knowns theta equals 90 degrees. Of course, we're being asked here for the rotational inertia and the mass, and so we'll do them one by one. So as we mentioned here, you cannot just go to the rotational inertia reference sheet to look up how to calculate the rotational inertia of a cylinder to do that here. They do not give you the mass, so we can't do that. So the first thing we got to do here is we have to solve for the torque. So the equation as given in the reference table for the torque is torque equals RF sine theta. Now, you could plug in 90 degrees if you want. I don't really care. But the sine of 90 degrees is 1. And so most times I'm just going to cross that out and write 1 and just rewrite the equation as the product of R and F. And so you could do that here. And so when we do that, we get here that the torque is equal to R, 0.330 meters, times the force, 250 newtons. Of course, if you plugged in the angle, you would have their sine of 90, but of course, sine of 90 is 1. And when you do that math here, I'm actually just going to show this over to the side so I have enough room. The torque we can calculate here as 82.5 Newton meters. So it probably wasn't obvious here that you had to find the torque first. Having said that, when they give you the value of a force and they tell you that force is tangentially applied, that's a big, big hint. That's super crucial information. Please keep that in mind. The reason, of course, why it's important to find the torque is because if we know the torque, which we do now, and we know the angular acceleration, which they told us, we can now go ahead and find the rotational inertia, or the moment of inertia I. And that really is ultimately the key to part A, is in recognizing that you need to find the torque to be able to find the rotational inertia. So I'll just go ahead and draw a line here to separate these things, and we'll say, well, Newton's second law for rotation says the net torque is equal to I alpha, where the net torque is what we just calculated, 82.5 Newton meters. I'll go ahead and add that to the list here. You don't really have to. It's not that big of a deal, but why not? We have this as 82.5 Newton meters. And so if we're going to solve this thing for I, all we need to do is divide both sides by alpha. So we have net torque over alpha. And that means we have 82.5 Newton meters, 82.5 Newton meters, divided by our alpha here, which is 0.940 radians per second squared. And when you do that math, again, this is kind of sloppy, but I'm going to write this over on the side just so I have the room. We have our rotational inertia I is 87.8 kilogram meters squared. So that's our value for the rotational inertia. And that's the answer to part A. Now, part B is a little straightforward now that we know the rotational inertia, because part B here is asking us for the mass of the object. And now that we know the rotational inertia, we're in business. Because if you go to the moment of inertia for common objects of uniform composition reference sheet here, this sheet that I posted last week, you can see here that every moment of inertia equation, especially for the more common objects, takes the form of mr squared, if the object is round at least. Even if it's like a rod, it takes the form of 1/2 m times some dimension of length squared. It's got to be that to make the units work out. And so here they tell us that this thing is a solid cylinder. It's important to realize that the solid cylinder and the disk are the same thing. Notice like the height of the disk, if you want to call it height, notice like this one's really thin, this one's a little thicker. That dimension doesn't really matter for the rotational inertia, because the rotational inertia is all about the distribution of mass from the pivot point. So the height doesn't really contribute. Now, obviously, a taller cylinder compared to a skinnier cylinder is probably going to have more mass, and so it will contribute in that way. But I just mean like the literal dimension of the height, like that length measurement, isn't a direct factor. Because they tell us this thing is a cylinder here, the equation we're going to want to use for our moment of inertia for this cylinder here is going to be 1/2 mr squared. And that really is all we need to be able to solve for this thing, because we have I and R. So the equation here for the cylinder, again, actually, this is a good one to remember. 1/2 mr squared is the equation for the disk. And so if we're going to solve this for m, we're going to want to multiply both sides by 2 and then divide by r squared. So we have 2I over r squared. And so we plug in here 2 times our 87.8 kilogram meters squared, and we're going to divide that by r squared. R, remember, is 0.330 meters, 0.330 meters, and we're going to square that. And when you do that math, you plug in all those numbers, you get 1,612 kilograms. But since everything given in this number has been 3 sig figs so far, we'll go ahead and call that 1,610 kilograms. And that's it for part B. It's important to realize the torque equation, RF sine theta, the Newton's second law equation, net torque equals I alpha, any of these rotational inertia equations, as well as alpha equals omega final minus omega initial over time, as we saw in that other problem in yesterday's video, they could all work together in a sort of rotational dynamics super problem. And that's a very important thing to keep in mind here. Notice this question really was attempting to be that kind of question, from them asking you in part C, what's the omega final if this thing is spinning 5 seconds? If the wheel starts from rest, what is the angular velocity after 5 seconds, assuming the force is acting during the 5 seconds? Well, of course, we know the angular acceleration. And now that they told us the time, the most obvious equation we can use here is omega final equals omega initial plus alpha t. And so to solve for this thing here, we recognize that the initial angular velocity is 0. So we just have omega final equals alpha t. And so we have omega final is equal to our alpha, 0.940 radians per second squared, times our time of 5 seconds. And of course, 0.940 times 5 is 4.7. I don't know why I said of course there. You're clearly going to need to use a calculator to do that math, but you get the idea. You just take the angular acceleration, you multiply it by the time, bada boom, bada bing. We have our final omega. And so that's it for this problem that was assigned in yesterday's video. And with that, we're basically done with rotational dynamics. And that brings us to the focus of the aim today, which is all about how energy stuff applies to rotation. So let's take a look. Now, what I want to do here is going to seem kind of odd to you because, well, it's no secret. This is the next slide. So the obvious question here is, why on earth are we talking about non-rotating things in order to have a discussion about how rotation can be understood in terms of energy? The basic idea is, remember, this whole unit we've been saying, everything you think about rotation has a lot of analogous ideas in linear motion. And so essentially what I want to do here in the beginning is just sort of refresh your memory about how this stuff works and ultimately use this as a device, a rhetorical device, to make a point. So this says here, the ramps shown on the left and the right are the same height. If block A has a mass of 10.0 kilograms and block B has a mass of 30.0 kilograms, which object reaches the bottom of the ramp with the largest speed? This is something like you definitely need to know for the AP test. They might not ask you something this straightforward, but it's certainly something you need to articulate. And now that it's the middle of March, now's as good a time as any to practice. So what I'd like you to do here is take 3 minutes to pause this video here. Come up with an answer. Come up with an explanation. You don't necessarily have to write it down. I'm going to write down a summary of the answer on the next slide. But I want you to think about what the justification would look like and why. And when you hit play, we'll go over it. So, a couple things to be noted here. The main difference between these blocks is they have a different mass. And so as I wrote here to start us off, both blocks start with gravitational potential energy at the top of the ramp and end up with kinetic energy at the bottom of the ramp. That much cannot be disputed. Object B has more mass and thus begins with more gravitational potential energy. As a result, object B is going to reach the bottom with more kinetic energy. I think I meant to say starts with more mass, but that doesn't make any sense. So let's just go ahead and cross that out. So what we're saying here is they start with gravitational potential, they end with kinetic energy, and object B has more mass, so it starts off with more gravitational potential energy. And that means it's going to reach the bottom with more kinetic energy. Now, some of you might be looking at that and getting a little nervous. They finish with the same speed. It's really important to remember that the fact that object B has more kinetic energy is only due to the fact that it has more mass. If we equate the initial gravitational potential energy to the final kinetic energy, we get an equation for the final speed. And that equation is the square root of 2g delta y. So if we really want to justify that with an equation, we would say the final speed is directly proportional to the square root of the height. Obviously, the 2 is the same, the g is the same, and so the fact that they have the same height means they have the same final speed, period, end of story. Having said that, it is really important that you understand how the energies compare, because they could always throw a curveball at you like that. Like, you all should know by now, if they start at the same height, they're going to finish with the same final speed. We've been saying that since free fall. But if they ask you which one has more kinetic energy, don't get yourself stuck in that trick where you're going to think oh, well, they have the same final speed, so they have the same kinetic energy. You have to be very careful about that. Object B absolutely has more energy, has more mass, so it has more gravitational potential. And because the energy is conserved, it ends up with more kinetic energy too. The difference is that the kinetic energy, which remember is given by the equation 1/2 mv squared, the kinetic energy has two parts essentially. It has the mass part and the speed part. And the object has more mass, so it's going to have more kinetic energy, but it's got the same speed. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, moving on, let's take a look at another question before we get to this rotation stuff. Obviously here we've got the same setup, but now the prompt says the ramps shown on the left and the right are the same height. Block A has a mass of 10, block B has a mass of 30. Which object reaches the bottom of the ramp first? Now, I think you know the answer to this. I would imagine you do. But I want you to think about what the proper way to explain this is. And what I want you to do is take a beat and think like, what does kinematics say about this? What does forces say about this? What does energy say about this? Because being able to explain the same answer using these different concepts is the name of the game when it comes to the AP test. You need to have all of these tools in your toolbox. So take a second to pause this video here and think about this answer. Think about what the justification looks like. And when you hit play, we'll go over it. Both of these objects reach the bottom with the same final speed. Both of these objects start with the same initial speed. They end up reaching the bottom at the same time. Now, of course, there's a lot of different ways that you can argue it. Energy, it's important to realize, doesn't tell us anything about the time. Energy can only tell us about the final speed, and we already went over the fact that conservation of energy tells us the speeds are the same. We should think about what forces says. Forces, if we did a forces analysis on this thing, this is an object on a ramp. It's being accelerated here by FGX, the parallel component of the block's weight, or the component of the block's weight parallel to the surface. And so these objects are going to have a different FGX. That's because they have a different mass, right? FGX is equal to FG sine theta. And so we can say here that FGX is going to be equal to mg sine theta. If the ramps are identical, the angle is going to be the same, but the mass of A is going to be less than the mass of B, and so FGX for B is going to be larger. The force accelerating B is going to be larger, but object B also has a larger inertia. So when we go to calculate the acceleration, we're going to get the force, if we just do F net over M, we're going to get this force here, mg sine theta, divided by the mass. And so the mass is canceled. The acceleration is just g sine theta. And so the fact that they have the same acceleration is very important. So it's important to realize what we're talking about here. An energy analysis tells us about the final speed. The forces analysis tells us about the acceleration. To determine the time in the most simple way possible, that's a kinematics explanation. Because that's what kinematics is all about. We don't really care why it's moving, we care how it's moving. And so I wrote here, both objects reach the bottom of the ramp with the same final speed after starting from rest. Since the average speed is equal to the average of the initial and final velocities, remember that equation is just v naught plus v final over 2. And here, because the initial velocity is 0, we can get rid of that. Really, the average speed is v final over 2. They got the same v final, so the objects have the same average speed. Since average speed is equal to the rate of change of distance, or v equals d over t, then the time is equal to the quotient of the distance and the average speed, right? T equals d over v. And they have the same average speed, and they travel the same distance, so it takes them the same time to reach the bottom. That's very important. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Now, this may seem like kind of a weird way to explain this, but I have seen enough AP scoring guides to tell you whenever you're asked about ranking the time it takes an object to travel a certain distance, you must think in terms of the average speed equation. The AP exam will almost always include that in the scoring guide. They're really interested in you talking about the average speed equation. That's something really important to remember. So take a second to pause this video here and write that down. And when you hit play, we'll start to talk about rotation. All right, and now we get to the good stuff. Let's say here, instead of these two blocks that we've been looking at this whole time, we have a hoop and a disc racing down a ramp. I wrote here, the picture on the left shows a hoop and a disc being released from rest. The hoop and the disc have the exact same mass. Which one will reach the bottom with a larger final speed? Which one will reach the bottom in a shorter time? What do you think? I want you to take a minute to pause this video here and think about this. Try to make a prediction. Which one's going to reach the bottom with a larger final speed and which one's going to get there first? And why? Really being able to think about the why part here is very important, because when we talk about the actual answer, it'll be good to reflect back on your reasoning and see which ways it was flawed and which ways you were correct, and so on. So take a second to pause this video here and think about that. When you hit play, we'll go over it. I think the key thing here to being able to answer this question is being able to answer the question, what is the biggest difference between the hoop and the disc? Now, some of you might be thinking, well, nothing. It said they have the exact same mass. But of course, how that mass is distributed between the two objects from its rotational axis is different. And so what we can say here is that the hoop has all of its mass concentrated farther away from the pivot point, which means it has a larger rotational inertia. This means the hoop resists changes in its rotational motion more, or at least that's what we said. The disc resists changes in its rotational motion less than, which means it's easier to rotate. We've already kind of said all this stuff so far. Well, let's see if it's actually true. And so here, let's take a look at a demonstration. Obviously, it makes the most sense here to just look at this. And so here we have this guy doing this exact experiment that we were talking about. It's going to try to full screen. There it goes. And we can see exactly what's going on. So he's got the hoop, he's got the disc, he's all ready to go. He might try to explain something. And so he's explaining some stuff, basically exactly what I just explained. Then he's going to let it go. And he's going to let it go. We all know they're going to come down. You don't need to tell us that. And there you have it. Oh, look at that slow motion graphic. It's clear the disc makes it to the bottom first. Let's just get an instant replay on that. Clearly, the disc makes it to the bottom first. And so everything that we've said about rotational motion in terms of rotational inertia thus far is confirmed. Take a second to pause this video here and write that down. And when you hit play, we'll move on. But of course, the whole point of this discussion is to talk about how energy comes into play. And so what we can say here is, since the hoop has a higher rotational inertia, what that really kind of tells us is that more of that initial gravitational potential energy is being used to rotate the object. And what that means is less of the initial energy is available to translate the hoop down the incline, which makes it get to the bottom slower. And because of that whole thing we said about average speed before, if it has a smaller final velocity, then that means it takes more time. Slower final velocity means slower average velocity over the same distance. Ultimately, what this demonstration is supposed to tell us is that our energy analysis has to work, right? And so if our normal energy analysis would say these objects have the same mass, that means they have the same gravitational potential energy starting at the same height, that means they should make it to the bottom with the same final speed, and they don't, well, then clearly we're forgetting about something. And what you should realize from this demonstration is that clearly there must be some sort of energy associated with the object's rotation. That kind of energy is called rotational kinetic energy. And that's what we're going to spend the rest of this video talking about. Take a second to pause this video here and write that down. And when you hit play, we'll move on. So as we mentioned here, objects have two kinds of kinetic energy. It has a translational kinetic energy and what we call a rotational kinetic energy. And you can sort of see how that plays out. Both of these objects start with the same amount of gravitational potential up here. But because this hoop is resisting that rotation more, a lot of that energy is being spent up just to try to get the thing rotating. And because that's the case, it's not going to move very fast because it doesn't have as much of that initial gravitational potential energy being used to make it move linearly. So I'd like you to write this under the heading here, total kinetic energy. Main point, objects have two kinds of kinetic energy. The kind of kinetic energy we've been talking about all year long is called translational kinetic energy. We never said that because there wasn't really any point in differentiating it because as far as we were concerned, there was only one kind of kinetic energy. So linear motion refers to the object being translated in space, kind of like how in geometry, when you did those translations, you were just like moving the shapes around. That's how you can remember this here. This is your good old-fashioned 1/2 mv squared. Of course, we also have now, as we saw from that demonstration, a rotational kinetic energy. And we call it a kinetic energy because rotation is like the rotational analog of translation when we talk about linear motion. Like the rotation is the motion. And so it's an energy associated with motion. And that means it's kinetic energy. And so as I wrote here, it's the type of kinetic energy associated with its rotational motion. This is the type of energy that we need to come up with an equation for. And that's what we're going to do next. Take a second to pause this video here and write that down. And when you hit play, we'll move on. Okay, so what I want to actually do here, and I'm going to try to go through this as quickly as possible because you don't have to know how this is derived, but I do think it's kind of interesting to see the way everything fits together. So I'm going to derive it. The first thing that we should say, though, is we should be able to come up with a guess. And the reason we should be able to come up with a guess is because what we've seen so far is that basically every equation we've seen for rotational motion has been just like a mirror image sort of everything we said about linear motion, right? It's just like you translate it, you quote unquote rotationalize it, and that's just the equation for rotational motion. It's like what we did with F net equals ma. You know, torque is the rotational version of force, et cetera, we got our equation. And so our guess here should be that the rotational kinetic energy, which we're going to actually put the subscript r on, is going to be equal to 1/2 the rotational version of mass times the rotational version of speed. Now, the rotational version of mass is the moment of inertia, or the rotational inertia, I, and the rotational version of speed is angular speed, omega. So 1/2 I omega squared, I think, is a pretty good guess at how this is going to look. But of course, we should see how that plays out and see if that's actually the case. To do this, we can start off with 1/2 mv squared. Now, as we know, mass in general is related to the moment of inertia by the equation I equals the sum of mr squared. Now, let's just assume this is just a regular old object, not a series of all these different point masses. So let's just say I is going to be mr squared. Well, if we solve that for the mass, then we get m is equal to I over r squared. Okay, so that's the mass part. Now, for the speed, we said here that omega is going to be equal to v over r. And so if we solve that for v, remember, this was our linear to rotational translation lesson, we had v equals r omega. Remember, we said if you want to linearize a rotational quantity, 9 times out of 10, you just take it and you multiply it by r. And that was the case for the linear speed, right? Because we said this equation makes sense too, because this equation says v is directly proportional to r. The farther away it gets, travels in a bigger circle, makes sense that its linear speed should be bigger. At least that's the way I always remember it. And so now that we have an equation for v and an equation for m, we could actually go and plug that in here. And so if we take our equation 1/2 mv squared and we plug this stuff into it, we get 1/2 m, which is I over r squared, times v squared, which is r omega, whole thing squared. And when you do that math, you get 1/2 I over r squared equals, and r omega squared is just r squared omega squared. And don't you know, the r squareds cancel, and what we're left over with is 1/2 I omega squared. And that's our equation for the rotational kinetic energy. Notice that matches up perfectly with our guess. Take a second to pause this video here if you want to write that down. And when you hit play, we'll formally introduce the equation. All right, so as we've already mentioned here, the symbol for the rotational kinetic energy is K with a subscript R now. And the equation, as we mentioned, is Kr equals 1/2 I omega squared, where, of course, I is the rotational inertia, measured in kilogram meters squared. Omega is the angular velocity, measured in radians per second. Now, what you should be thinking here is, well, what should the unit of the rotational kinetic energy be? And the unit should be joules. It's an energy, right? So how is it that we get that? Well, you get that simply by combining these two terms. The most important thing to remember is that when you are combining these units, you want to treat the radian as a 1. And so when we take 1/2 I omega squared and we plug in the units, remember, half doesn't have a unit, so we don't really care about that. We have kilogram meters squared times radians per second, and then whole thing squared. And so we get kilogram meters squared. We treat the radian as 1, and so we get 1 squared over second squared, which is basically just going to be 1 over second squared. And since that gives us units of kilogram meters squared per second squared, that, remember, is a joule. And so the unit for rotational kinetic energy, I think pretty unsurprisingly, is a joule. And so the unit here, of course, is a joule. And like all other energy-related quantities, it's a scalar. Take a second to pause this video here and write that down. And when you hit play, we'll move on. All right, now before we go for today, I do want to use this stuff to solve a problem. So let's take a look at a problem. This problem looks like it's from your packet, but it's actually not. It's from the older version of one of the textbooks in your packet. So the one actually in the packet has different numbers. So I just want you to write down the notes for this problem. You don't have to copy down the problem. It says a bowling ball with a mass of 7.3 kilograms and a radius of 9.0 centimeters rolls without slipping down a lane at 3.3 meters per second. The question here says calculate the total kinetic energy. That's a very important thing to pay attention to here because they're telling you it has a total kinetic energy. The reason why that's important here is because if a ball is rolling and moving forward, that means it has a linear and angular speed. And so that means here the total kinetic energy, and I'm sure you're thinking it's kind of weird that I'm writing TOT for total, is going to be the translational kinetic energy, K with the subscript T, that's why you write TOT for total, and the rotational kinetic energy, K with the subscript R. Now, I know some of you probably have the tendency to ignore some of the things I'm saying in some of these videos and just doing things on your own. But I really recommend you watch this very carefully because when it comes to the problems we're going to be solving tomorrow, you have to have this mastered. You can just calculate the translational kinetic energy 1/2 mv squared and calculate the rotational kinetic energy 1/2 I omega squared. It's a horrible idea, in my opinion, because you need to be able to do this skill that I'm about to show you right now in the problems tomorrow. So first, before we get into that, let's just write down the knowns. They tell us here that this bowling ball has a mass of 7.3 kilograms. They tell us its radius is 9.0 centimeters, so 0.09 meters. And they tell us here that the linear speed, and you can tell it's a linear speed because it's in meters per second, is 3.3 meters per second. We're being asked for the total kinetic energy. Now, as I mentioned here, this thing does have two kinds of energy, and so we are going to write an equation here just to start us off. The total kinetic energy equals the translational plus the rotational kinetic energies. And the main point here is that you want to do substitutions to make this work. The first substitution we're going to do is the equations For the translational kinetic energy, 1/2 mv squared, and for the rotational kinetic energy, 1/2 I omega squared. And at this point, you need to sub in, or at least it is highly recommended, you have to do it for tomorrow, but here it's highly recommended, you have to sub in two equations. You sub in the equation for the rotational inertia, and you sub in the equation for omega. If you look on the rotational inertia reference sheet, then you will see the rotational inertia of a sphere, which a bowling ball is basically a sphere, is 2/5 mr squared. And so we're going to want to substitute 2/5 mr squared for I. So we're saying I here is 2/5 mr squared. We are also going to want to substitute an equation for the angular velocity. As we said here before, the easiest thing to remember is V is R omega, because V gets bigger when R gets bigger. So that means omega is V over R. Very, very important note here, because watch what happens when we do that. I'm going to say here the total kinetic energy is equal to 1/2 mv squared plus 1/2 of I, which is 2/5 mr squared, times omega squared. Omega is V over R, and so that means we're going to have V over R squared. The key detail is what happens in the next line. We have 1/2 mv squared plus 1/2 times 2/5. Remember, when you multiply fractions, you just multiply the tops and multiply the bottoms. So we have 1 times 2 is 2, 2 times 5 is 10. So we have 2/10. We'll simplify that to 1/5 later. And we have here mr squared times v squared over r squared. Notice here, this r squared is going to cancel that r squared. And so we just get 2/10 mv squared. And that's the beauty of this approach, that now what we have is a fraction of mv squared plus another fraction of mv squared. And that means when we add these two things together, we'll be able to have a nice, neat, tidy little equation. 1/2 and 1/5 cannot be added together directly. We need to find the least common denominator. The least common denominator was actually 10. 1/5 is 2/10. 1/2 is 5/10. So that means 1/2 plus 1/5 is 7/10. And then we have mv squared. That is a super crucial skill for these kind of problems. When it comes to actually doing the ramp rolling problems that we're going to do tomorrow, you must know that. And so we'll say here the total kinetic energy is 7/10 mv squared, where m here is 7.3 kilograms. And then v is going to be that 3.3 meters per second they gave us in the very beginning of the problem. Remember, we got to square that like we do in the original one. And we get a total kinetic energy when we do that math of 55.6 joules, which to two sig figs we can call 56 joules. To summarize, when we write out the total kinetic energy equation, we sub in the actual rotational inertia equation for I, we sub in V over R for omega, and we combine. It will always be the case for the original rotational kinetic energy term that the R's will cancel. That's an interesting little relationship. That will leave you behind just a fraction of mv squared. You need to find the least common denominator to add them. And when you do that, you'll have some fraction, and that fraction ultimately will depend on the shape, because this fraction differs for like the hoop, the disc, the sphere, whatever, some fraction of mv squared. If you cannot do this for tomorrow, like when we get to the point where you actually need to do it, you're in trouble. And so just very quickly before we go, I want to show here, notice, if you just actually went through the trouble of calculating I using the equation 2/5 mr squared, you would have gotten this super annoying number here, 0.023652 kilogram meter squared. And if you actually went through the trouble of finding omega, you would have done that by taking V over R, and you went through and you did that whole calculation. You would get 56 joules. But what I'm telling you is that this approach, getting some fraction of mv squared, is really what you want to do. Because tomorrow, you absolutely have to. There is no choice in the problem tomorrow. And so what I want you to do for today is demonstrate that you know how to do this. Here's a problem. A 140 kilogram hoop rolls along a horizontal floor so that the hoop's center of mass has a speed of 0.150 meters per second. The question is, what is the total kinetic energy of the hoop? That's what I'd like you to submit for today. I look forward to your answers, and I will go over it first thing in the video tomorrow. Have a good one, everybody.